Just swung open again. Thank you, Campbell. All right. Terrible. Terrible. Good and no. 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 Good enough. Date is the 22nd of the 11th. Okay. Let's start with a very brief chat, okay? So gravity is a super weird concept, and every concept or every way of conceptualizing gravity that we teach you will probably be wrong. The reality is we don't know the full picture with gravity. It's the one thing that doesn't fit in with the standard model. So you may have heard of the grand unifying theory, which is this idea that hopefully one day physicists will have a way of unifying Einstein's theory of general relativity, which is our understanding of how gravity behaves, and quantum mechanics, which is our understanding of very, very small things. Okay, right now you cannot combine them. We do not have a model for accurately predicting gravity on a quantum scale or quantum on a large body scale. So the reality is this is an unfinished science. But if we go back to 1400s, back to Newton days, Newtonian mechanics are pretty well understood, and they've been extended on quite a lot, and most of those models are still really successful. Okay. Now, there's two key ways we will talk about it. We will talk about general relativity, but it's actually not going to be in your syllabus at all. So you're not going to cover any actual Einstein general relativity. You'll do special relativity, which is about things that are moving really fast, having dilated times and contracted length. You will not be talking about general relativity in any assessments, okay? It can come up in some, which is why we mention it and sort of establish a bit of an understanding of what it is in case it does come up in a research investigation or something, but it's not going to be assessed, okay? The other way that we'll talk about gravity, which is correct, is in Newton's laws of universal gravitation, okay? Very, very simply, Newton's law of gravitation says this. Totally new topic. Oh, we're still topic 1? Hang on, I've got your syllabus here. This is still topic 1, yeah. Gravity and motion. Topic 1 will take us to the end of the year. The end of this week, we'll finish it, so. Yeah, we'll cover orbits. Very briefly, to be fair. We will review it when we come back. Yeah, well, we'll go through it in enough detail that you'll basically get everything, but we probably won't have enough time to consolidate, so we'll come back to it. Yeah. All objects with mass experience gravity and impart a gravitational force on all other objects. Pop quiz. While you're writing this down, think about this. Which has a greater gravitational force affecting it? The Earth from the sun, what the Earth is experiencing due to the gravity of the sun, or what the sun is experiencing due to the Earth? Which mass experiences the greater force of attraction? Okay, so sun's very massive, imparts a greater force. Equal, could be equal. What else do we think? What do we think, guys?
Depends on distance.
Depends on distance, but the Earth and the sun are the same distance apart. So distance is constant. Would Earth, if we were to draw force vectors on the Earth, would the force vector be greater on the Earth, or would the force vector be greater on the sun? Right. So intuitively, we're all pretty aware that, of course, the sun invokes a stronger force of gravity, except we're wrong. Yes. We're wrong. Why are we wrong? Alex? Right. Remember, guys, when we have a feather, feather's a bad example actually, a golf ball and a bowling ball, okay? And we are going to ignore air resistance. They fall at the same speed. Why are they accelerating at the same rate if their masses are different? We know that things with more mass have more inertia. That means they resist a force's efforts to accelerate them, okay? If I flick my water bottle, it won't go very far. If I flick this pen, it will. Same amount of force in each case, but the acceleration on the pen is much greater because the mass is less. If a bowling ball has much more mass, why does it accelerate at the same rate than a golf ball when I drop them? It experiences more force because gravity is dependent on what? The mass. Now, generally, we talk about this rule one-sided. We say that things that are falling to Earth are being affected by the mass of the Earth. There's a gravitational force affecting them. But it's actually a two-way equation. When you throw a golf ball into the air, that golf ball has mass, and all objects with mass experience and impart the force of gravity. So when you throw that golf ball into the Earth, it's attracting the Earth up to it. The golf ball applies a force of gravitational attraction to the Earth to attract the Earth back to the golf ball. Equally so, the Earth imparts a force on the golf ball. The force is the same for both the golf ball and the Earth. It's maybe like 0.1 newtons. That golf ball is attracted to the Earth with 0.1 newtons. The Earth is attracted to the golf ball with 0.1 newtons. It's obviously not 0.1 newtons. We actually know exactly what it is, but anyway. Whatever it might be, the acceleration is different. The Earth, negligible acceleration because it's very massive, so it has a lot more inertia. It doesn't get accelerated by this tiny little attractive force. The golf ball, very, very little mass, does get accelerated by that tiny little force. The sun and the Earth, the sun, pretty big mass, relatively speaking. Understatement? Yeah, we could use a bit more emotive language about it, right? Friggin' humongous, right, compared to the Earth. So the force that it experiences from the attraction of the Earth, because there's no doubt that the Earth has an attractive force, is there? Because it's attracting the moon quite successfully. It is trying to pull the sun to it, just as the sun pulls us to it. It's just that the sun is more massive, so its acceleration is less. Also, thankfully, we're in orbit around it. If we were just sitting out here, we would move very quickly towards it, and it would move very slightly towards us, and we would collide. Because we're moving around it, the sun stays centered, because the acceleration that we're imparting goes around in circles and cancels itself out once a year. It's a beautiful dynamic system, isn't it? Right? Yes. Is also, yes, but it's central and mostly stationary relative to our orbit. Yeah. Okay, check this out. We're going to introduce some notation, a formula, and a representation. So diagram, nice and big so you can notate. Space for a formula down the bottom here for me. This is lowercase m. Case sensitive, please. This is capital case M. This is the force. The force. This distance is our radius. Yes, you heard me correct. Radius, we call this. Why? Because we're mostly going to use this for orbits. So to be very clear, those forces are what? Yeah, they're balanced because they are equal and right. Okay, this is the rule we're used to with Newton. You push on a table, that table pushes back. Okay, if we're in if we're in perfect uniform circular motion, that distance, that displacement is not changing. We can say that we're not accelerating into or away from the object. Now, of course, we know we have a centripetal acceleration, but that only depends on direction changes. Okay, the magnitude of our distance is not changing. You can talk about displacement as not changing. You can still realistically talk about these objects as being, relatively speaking, stationary to each other. Mm-hmm. What causes gravity? That's what we don't quite know. So there's something called a Higgs field, which is a field we believe permeates our space. There's a particle called a Higgs boson, which we believe is the particle that gives objects mass. In other words, gives objects the ability to interact with the Higgs field. And we believe when the Higgs field is manipulated, it can change the... So instead of space being a perfect sort of grid, right, like these gridded lines, if we imagine the Higgs field can distort how space is warped, and so it could squeeze these two lines together, just like sort of stretching a sheet of fabric or pinching a sheet of fabric together. So it can change what we talk about as being two straight lines. So that's when you think about a bowling ball and a trampoline making a circle. That's kind of wrong, but that's the current sort of going theory. No. Yeah. So that's sort of talking about the idea of warping or distorting space as a fabric, and that's what we think of gravity as being. It's not technically a force at all. Okay, is that diagram fine? No questions about that? Capital M, lowercase m, really important. Here's your formula for this. Oh, I'm blue. Dabba-dee-dabba-die. G M M over R squared. What is the capital G? Go to formula and data book and find it for me. It's in there. It absolutely is a constant. where G equals, what's it called? Gravitational constant? Now, what is that capital G not? It's not gravity. It's not lowercase g. Thank you, Alex. Yes, you are correct. It is not lowercase g. What's lowercase g again? Exactly. Acceleration due to gravity. Due to what gravity? Only on Earth. It's an average for the acceleration of objects due to the gravity from Earth. It entirely depends on which planet or other mass you are talking about. This is the part that we generally leave off. That capital M is the body that is imparting the greatest amount of force. Now, it's actually arbitrary. You could swap between the two M's. You can do this calculation with M's that are exactly equal to each other, okay? But there are two masses involved for gravity, right? If a tree falls in a forest and no one's around, does it even make a sound? If a gravitational body is in a vacuum with nothing else around, does it even have gravity? Who knows? Maybe not, right? It's not until another object comes into that gravitational field that we see that. All right? So generally we ignore that capital M. It's just Earth. It gives us the little g. Things are easy. Things are not easy anymore. We're in space. All right. Can I go to the next page? A little bit longer? Speak now, forever hold your peace. Either M to either object. Generally, convention is the capital M goes on the bigger object, but it literally does not matter. Why is orbit a thing? Because there's an attractive force inwards, a centripetal force, which constantly attracts them inwards, but they already have a velocity moving in a tangent. Because at the creation of the solar system, there was a bunch of chaos and a bunch of motion, and anything that wasn't in that perfect ratio of acceleration due to its mass and its velocity would just fall into the sun and disappear, so we don't see it anymore. But once upon a time, there was a bunch of things that weren't nice, smooth orbits. Every solar system, that's how it would have had to happen. It would have been this huge cloud of dust and energy, and as everything sort of settled into place, the things that weren't perfectly at the right distance with the right mass would just fall into the sun or float off into another galaxy. What do you mean? No, so the question would have to stipulate, like calculate capital M, the mass for this one. They would have to specify. Yep, yep. Yep, and the centripetal force in that case is gravity. Mm. Thank you. All right, I can move on, yeah? All right, let's go, guys. Couple of dot points. Max, make sure you're keeping up on the notes, mate. You can talk to me about Terraria if you want, but later. Mr. Nielsen, do you have a favorite class? No, I don't pick favorites. Oh, wait, do you mean I mean like as in like the I thought you were asking me if I have a favorite student class. I said you can talk to me about it at break time. Annie, you got these notes down? Did you say yes? Because you wouldn't lie to me, would you? If I come over there, I'll see it, right? Hmm? I probably need to get better at actually editing them, but right now it's just raw, unfiltered upload. You'll do my editing? I can't pay you, that's illegal. What, that I can't pay a student? It is directly related. It's literally a recording of their lesson. All right. Ready for a pop quiz? You have 1 minute to make sure your notes are down and then read this worked example. I'm going to ask you the notation and the answer. So I'll say lowercase m, what is it? And you'll tell me. I'll say capital G, what is it? And you'll tell me, okay? Feel free to draw a diagram, just like the representation I gave you earlier. 40 seconds. You can copy the example down if you're waiting, but I'm about to pop quizzes in 20 seconds on the key info from that question. Right, here we go. Pop quiz. Cody, give me an M, lowercase m. Nice and loud, I can't hear you. Cool, lowercase m is 7.35 times 10 to the 22. Anyone disagree? What do you disagree with? Lowercase m. That is the lower value. Cool. Yep. Could you do it the other way around? Yeah. Absolutely, you could. But I agree with Cody's use of convention here. Capital M, then, please, Michaela. Not if it's lowercase m. He said it was lowercase m. Lowercase m right now is 7.35 by 10 to the 22. So what's capital M? Definitely. Cannot be both, yeah? You've got to make sure whatever you do, they're separate. And Max, radius. R. Right, so you need to switch on for me, man. When we were looking at this picture before, we established that the distance between our two masses, and as we discussed in that dot point, we can consider it from the center of mass. That distance is, what's it called? Radius. Cool? All right. So then you just plug that into your formula and you solve it. You don't need me for that, do you? Easy, right? How easy is gravity? Crazy. Well, this question. That's what you should get as an answer if you haven't done it already. Oh, hiding it. Oh, what have I done? Get rid of it. Get out of here. Get your answer. I'm not doing it for you. Doing your own examples these days. Yes. I agree. I think. Remember, key things we're looking for marking these, for getting this fully correct. We are looking for statement of formula, correct substitutions shown. I should have a step that shows me that substitution. And then correct calculations to give an answer with units. Do we need to have a conversation about what the units will be? It'll be newtons as long as you calculate everything in SI units. Remember those calculators, you've got to be careful of your order of operations. All right, here's your answer. Interestingly, they preserved 3 significant figures despite the distance being given in 2. Remember with constants like g, don't consider them in your sig figs decisions, okay? Theoretical constants you can assume to be infinitely accurate. Yep. What? What's your point?
3.8 there, but then in the sub.
It's probably a typo in the textbook print. It's probably meant to have a 0 there for 3 sig figs specifically. Yeah, if you did in 2 sig figs, that's fine. Cool. Remember, that is actually technically your example, even though I was too lazy to actually do it and you did it yourself. So, if you didn't do it right, make sure you now rewrite it nice and neatly and clearly, acknowledging that you need to demonstrate, and you should show this in your example, formula, substitution, solve. One point that could be worth making, for those of you who are lazy like me and want to save time, capital G, and for that matter, any constant value that is given in your formula and data book does not need to be restated at any point in your calculations, okay? If you're using capital G or lowercase g or whatever else, you can just you can just leave it as the symbol all the way to the final step where you put it into a calculator. You never have to write the actual numbers. Just as a time saver. For a lot of you, you'll probably prefer to just always write the number because sometimes it's just easier to see it like that. And that makes it easier then to break down your calculations bit by bit, but you are not required to. All right, I want to talk about one last thing very quickly. So shift your attention back up to here for me. There's a really important point to make about this. Now, don't copy this down. I just want to talk about that formula. F equals G, constant value, pretty meaningless, right? Just a number. Capital M times by lowercase m, just the product of the two masses, pretty straightforward, linear relationship here, right? As the masses increase, the force will increase in direct proportion, right? This is where things get kind of interesting. What does this tell me about the relationship between force and the distance between the objects imparting or experiencing that force? Have a think about it. Try to state it in a mathematical way. How could we state the relationship between force and the distance between those objects? So if I had this situation, this is lowercase m, this is capital M, this is radius, but then we went same m's, exactly the same objects, some number greater than radius. What would that affect the force? What would be the effect of that on the force? Let me pick on someone. Destin. What does this formula tell us about that relationship? So let's remember, this is going to be constant, all of these three things, right? So we can say F is going to be proportional to some constant value. Times by what? What am I left with? If I take all of that out and just make it a constant value K, what am I left with? Not sure? Sure? Nicola? Over R squared. So can you summarize what this means, Nicola? Makes the force smaller. Right. How do we say that mathematically? Max? Inverse squared proportion. So what does that mean? That means if we have a radius of 2, we get the force is a quarter, right? 1/4. If the radius doubles to be 4, our force does not double. That is not double. The force does not double. The force has quadrupled inversely. So it's 4 times smaller when the radius is 2 times bigger. inverse squared relationship. So what that means is you get this massive fall off with gravity, but it's never zero. Theoretically speaking, it's never zero. Radius just gets bigger and bigger, and the amount of force gets smaller and smaller. This is one of the fundamental problems with gravity that we can't quite wrap our heads around. Right now, you have an attraction to a little alien's marble that he's playing with on the other side of the galaxy. Hey? Yeah, so it does get a little bit messy when you actually start talking about that scale. And what comes more into play than gravity whatsoever is the expansion of space and dark energy and dark matter and the role it plays, and all sorts of complex things. But theoretically speaking, our current understanding of gravity is that it never stops. And that's actually the case, technically speaking, with all forces of the universe, all fundamental forces. There's no 0 point. They just fall off. Right, yeah, absolutely. Yep. Let's take a brain break there, and then we'll jump into our exercise, yeah? Give you a minute? Yeah, we can play Silent Ball. Might stop the recording. All right, there we go. There is your exercise. This is the check you're learning from your textbook. Question 4, 5, 6, and 8. Be aware some of these questions might require that you know the mass of the Earth and stuff like that. If that comes up, just let me know. But I think everything you'll need will be given. It just might not be given in the question you're asked it. Just keep that in mind.